Let's see, testing sound.
Let's see, testing.
That worked. All right, sound works. Let's see here. Well, I'm going to be actually starting soon. I just like to give a little bit of time ahead of time so that people can join if they would like. And yeah. Did I spend the time? This is an unusual day for me to do it. I'm doing it today mostly because I accidentally missed yesterday. And yeah, that's mainly why I'm doing it. And I accidentally missed yesterday, which would also have been an unusual day, but that was because I also accidentally missed Monday. But hopefully, I'll also be streaming tomorrow. Uh, though I don't know that there's any of you watching to know that right now, but what the heck. There we go. All right then. Today we might actually be playing around to see what we can use agents to accomplish. Because I have a rather repetitive task that an agent should be fairly good at making work. And so I'm going to going to do that. Anyway, I think that it's time to switch over. Oh, why are you being like this? There we go. All right. So I'm going to try and get AI to do something, but first we're going to find out what were we doing to this last? Because I was adding some stuff for doing variable declarations. To this thing, and I had just put in a simple hack to kind of make it work with the existing identifier system, I think. Let me check to find out whether all the existing tests run in this current state. They do not. No, they do not. Well, that's interesting. So I added variable declarations, and then I added some kind of system to sort of make variable declarations work within the existing framework. And part of adding variable declarations was adding, I believe, the var keyword. Yes, the var keyword. Maybe that's the wrong keyword. That betrays I'm probably going to not use immutable, like switch it to immutable variables at some point in time. Although, I don't know, maybe I will do that. Nobody else is using this thing. Who knows what I will do. And then maybe I'll switch the keyword so that it isn't var anymore. But right now, keyword is var. And so a variable declarations consists of what is the... So that's what this looks like, parser.hpp. Up here, var declaration, var identifier equals expression. So this is, yep, you have to have the var keyword, then you have an identifier, and you say equals, and then you have an expression and not a semicolon. Okay. And then you have an assignment. identifier equals expression. Let's actually run this in debug mode and find out where it really... Yeah, this is happening in evaluate. Here in evaluate, and then we're doing the statement list one, so we're evaluating one of the statements in the statement list, and we have an assignment statement here. And the assignment statement is no, this is the simple evaluator. The assignment statement is x and then equals something, which makes sense given the test that's being run, which is figuring out where this test actually is not trivial, sadly. So I think there's some inline functions involved. So it's hard to know exactly where in our, because we don't care about this, we don't care about that, we don't care about this, we don't care about that, care about this. And we're on some line of this and we don't know what. But we get x equals blah. So we're looking at stack. What's on stack? So we're looking at this stack. Oh, and we don't even have something pushed onto the stack. But we should, part of this one here, not assignment statement, but the one above it. This one should have been, this only does it if there's identifiers. Okay. So there needs to be one for the but the topmost one is always going to be, I know what we do here. This is terrible. Or stack empty. And we push on something here. There. Now let's run these tests and see what happens. Okay. Well, that's very interesting. We're still getting a segment fault. Well, that's very odd. Okay, let's look at SL here. Well, that's completely kosher. So identifiers is in fact referring to a real thing. Right? Oh. Identifiers isn't pointing at a real thing? Oh, it's a unique pointer. Oh, I see. Yep. That's the right thing to do here. All right. Now we're getting a segment fault again. Okay. This stack. Oh. Yeah. Not the right way to handle it. Okay, what I just didn't help. It was a band-aid on a problem that I should not have. Yeah, shouldn't have done it. Shouldn't. This is the wrong way to handle this problem. What should it do? Yes. So simple evaluator is a. Let's go find the go to declaration. It's defined here, has a default constructor. It is going to need a constructor that is a little more complicated than the default one. All right. So, var decal, da 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 da. Okay, let's see here. We're looking for places where infix is mentioned, and in this file, it's only mentioned here. I see. That's kind of what it's doing. There. Okay, there we go. None of the tests exercise variable declarations. And I put in a little bit of the machinery for allowing stack frames, and also there's going to be static scoping. So that's going to be interesting, how static scoping and stack frames will interact. I should do a very simple demonstration of static versus dynamic scoping, what they look like. Because although, again, dynamic scoping, nobody does that anymore. Nobody. The closest that we've come to dynamic scoping in the past 25 years, as far as I know, is Python with its weird global thing. But even then, I don't think we're doing dynamic scoping precisely there. Yeah. But it is a little closer. And so I don't know how relevant it is, since everybody does static scoping. And in fact, dynamic scoping is incredibly confusing to work with from a programmer's perspective. And there's a reason why it's been abandoned. You can't just look at the program text to figure out where a variable is. You have to analyze the control flow of the program to figure out where a variable's value is. And that just gets to be too difficult. All right. But anyway, what I've done here is kind of a hack that introduces essentially a global stack frame. And all the variables that get dynamically created now get shoved into the global stack frame. And this is ugly, and I need to think of a better thing to do than this. In fact, it shouldn't be done. Basically, attempting to use variables before they're declared should simply fail, is what should happen. So, yeah. Anyway, that's going to require actually a lot of machinery in the parser to make that happen. And what I'll have to start doing then is I'm probably going to have to shift it from using these stack frames in this way. Like the stack frames are no longer going to be the stack frames. The stack frames instead are going to be work in a completely different way. Like you aren't going to be storing names in them anymore. Anyway. Yeah, we're going to leave off for this for now. We're going to I need to have a pre-commit hook that does this for me. All right. I need to research Mercurial pre-commit hooks, and I need to add one so that I can do commits and then have the pre-commit hook fail if instead of doing all this laborious, let's check the number of characters, you need to have it just fail anyway, if it's not in the right format. So, now that we've done this, we are going to look at a change that I made to some of the tokenizer tests, and then change the rest of the tests to check on it, to do it that same way, because this one is just painful to look at, and yes, there we go. So one of the things we're going to do, not generate code, we're going to blame. Annotate. Well, yes, but I want to know more than that. What's going on here? Oh. Yes, this is just a new test that I added. Okay. How do I get rid of this? So we need to look up here. Yes. I see. If you hover, a little pop-up will appear. So we're going to see if AI can do something for me. So let's pop up the AI thing. Oh, it wants to update Sea Lion. I'm not going to update Sea Lion right now. All right. A test vector of tokens. So let's see if the AI can do this for us. Judy is working away. we are going to turn off the annotate mode now because it is no longer helping us. Annotate mode, what it does is it tells you on a line-by-line basis which change set, which commit a line was changed in, last changed in. So it's really good for figuring out who did something to a piece of code and what other things they might have done at the same time that are still surviving. Yeah. And here, the reason I wanted it is because I was going to look at, okay, I have a test that has already been changed to use the new style. I want to know which change set it's in so that I can tell this AI, hey, look at this change set. Do that to everything. Because I figure that giving the AI a nice template of what needed to be done instead of just telling it to do it in sort of English and hoping that it figures it out would be better. More specific instructions, hopefully. LLMs are not necessarily things where you need to give them specificity precisely, but yeah. In this case, I felt that that was probably the best thing to do. One of the things here is it's telling us about the changes that it's making to it, and you can see the reason why I wanted to do it. Takes up many fewer lines. And I mean, it's not just that I wanted it to take fewer lines. That's not necessarily, in and of itself, a good change. The reason why, in this case, it is a good change is because it makes it actually easier to understand the function when it's fewer lines. All the extra lines, there was just a lot of boilerplate that was repeated over and over and over again. And it would just be nice to not do that. Yeah. And also back to what I was doing with stack frames. So there's two problems that I have, and one of them is a parse time problem, and one of them is a runtime problem. At parse time, I need to keep kind of a nested framing of what variables are available in the scope, because the scopes all nest inside each other, right? And so when you refer to a variable, it's going to check in the inner scope and then the next inner scope and so on and so forth. But then when it actually figures out what variable it's talking about, that variable has an identity quite apart from whatever name it was given. The name is just a way to reference the variable. It isn't the variable itself. The variable itself is just a block of storage in memory someplace, right? And your use of that name is convenient, as a convenience for you, the programmer. So that's what I needed to do. Is as it was building up the nested scopes, when it encountered a variable, it needed to look that variable up in the nested scope declarations to find out where the declaration, what variable really is being referred to, and then it needs to change that reference to an identifier to being a reference to that variable, right? The abstract idea of the variable, not the name, which is the name is kind of a way to reference the variable. And then at runtime, there's a different kind of thing that happens because, well, this won't actually happen for this code because there's no functions and therefore no recursion, or even call stacks. In a normal program, you have call stacks, and call stacks will result in a reference to a variable, a local function variable. That variable is going to have a different identity every time the function is called, or a different place in memory that it exists. The identity, as far as the parse tree is concerned, is going to be the same, but the identity at runtime is going to be different because every time the function executes, a new stack frame will be created that contains new instances of all of the local variables for the function. And so I need to handle both of these kinds of nesting at different times and in different ways. And I added the stack frame notion to the simple evaluator. But honestly, the simple evaluator right now doesn't need a stack frame. The stack frame is something that's a runtime construct when you're doing function calls. You don't need stack frames when you don't do function calls. And so, yeah, I don't need what I need is a variable registry, kind of. I need kind of a thing for how many slots, variable slots I need total. And then what variables mean which slots at which time will change. Yeah. But at parse time, I need some kind of frame construct to describe the various levels of the statement list hierarchy that are being traversed. Yeah. So we'll figure it out. I think that the stack frame that I have here is totally wrong for what I'm doing with it. I need something other than this stack frame concept here. Now Python, interestingly enough, we could go back to Compiler Explorer. In fact, actually, let's do that. That might be very instructive to explain to you what's going on here. So here, I hope this is large enough. Let's make it a little bit larger. Okay, so we are going to do something else here. We are going to, oh, yes. And then this is going to be Python, right? And there, okay. Here's some examples. Right? Okay. So you notice here, right? This right here is the function. The code, it loads the code object square. Yeah. Then it makes functions. Then it stores name, square, load constant and return value. Okay. But that's this code here that's executed at module load time, right? So this is what the module is doing. The module is taking this code object and it's stuffing it into a global variable by the name of square. And here it does a very similar thing. Like You see here store name square. Here it's doing load small int 23 store name foo. And you notice how it has these integers at the end of the store name. So this integer kind of refers to is kind of a different way of referring to the name, right? So it kind of assigns integers to these variables as the module when it parses the module. It assigns integer values to these variables, and then it refers to them by those integer values here in the code. And then let's look at the disassembly of the code object that it's stuffing into square. So that this is the actual text of the square function, right? And resume 0 is basically a way of going, okay, everything here, this is nothing. The module is over. None of this stuff needs to be run at module load time. All the rest of this stuff is stuff that's kind of data for the module. But part of that data for the module is, of course, more code. The code object in particular, the load const 1, right? And this is const 1. And load fast barrel 0, 0. So basically, it's grabbing something called 0, and then it's calling it's loading the global foo, and then it's calling plus, right? So it doesn't even reference, like here it says 0 is num, but it's saying in the code it actually says 0. So the Python, the parser that went through this to turn it into this stuff here, it actually looked at num and went, okay, num is variable 0 in this square function. And so if I did it like this, I could do this. I can say right, and then I could say bouncy, and then it will get recompiled. So notice how this didn't change at all, because this is all exactly the same. I changed the inside of this function, and therefore this code object constant right here is what got changed. So load fast barrow 0 num, load small int 5, binary op plus. So basically that's this line here. So it loads the 0th variable, it loads the small integer 5, and then it adds them together. And then it stores them in variable 1. You notice how now it has variable 1, which happens to be bouncy. And then it does load fast barrel, basically a way of doing 2 load fasts all at the same time. And then it does binary op star, right? Let's multiply them. Then it does load global foo, basically load the 0th global, and then binary op plus, right? Add foo and bouncy. And so this is Python, as you can see, turns all of these variable names into numerical references. And so that's kind of what I need to do in my code as well. And part of what happens when this code is executed is a stack frame is created that has spots for these local variables. And it has slot 0s and 1s and whatever for these local variables. But it also has global variable slots. And so I kind of need to turn this stuff into, it's still doing it. All right. Anyway, yeah, I finished my explanation here, and then I was just going back here to check on the progress of the agent in carrying out my wishes. But this is a lot faster than it would take me to do the same thing, provided it's doing it correctly. I'm going to have to look this file over carefully to make sure that this is basically correct. And one thing, of course, will be if it only changed this file and all the tests pass, my job of making sure that it did it correctly is going to be a lot easier because I'm not going to have to painstakingly verify each of these lists. I'm just going to have to verify that there is a list, that the expression, the thing in the string didn't change. It didn't change the string. It just added this list, and then it does this require that. As long as it did all of that, I don't really have to care whether the contents of the list are correct or not, because if they weren't correct, the test would fail. So yeah, having good tests. And of course, one of the things the LLMs do, or these agent-based things do, is they will in fact run test suites that you have after they make changes to try and make sure that their changes don't break tests. I actually have a different piece of code that's a lot more. It's not more complicated. This code is more complicated in a certain way, like the algorithms involved and the data structures are involved are significantly more complex. The other code is complex for a different reason. The other code is complex because it's working with very low-level system constructs and actually has some direct inline assembly. And one of the things I would like to do in that code is sort of mark out certain regions as being their contents must reflect what the program model says their contents is. So one of the things that can happen in C++, which I can't demonstrate things right now, but one of the things that happens in C++, and actually I can kind of demonstrate it. Let's go back to doing C++ here. Okay. We're using GCC trunk and we have square here, right? So what if we did right? And we're also going to say just to tell it that this function might get actually referenced by something. Oh, it was smart enough to realize that this function will never exit, and so that it's an infinite loop. You notice how this code here doesn't seem to resemble anything that this function does. Optimizers are allowed to do a whole lot. And this optimizer has looked at all this code and realized this code will never complete. And therefore, I can just replace it with an infinite loop. So there, much better. Now, notice how this code still doesn't have a call instruction in it, despite the fact that I'm actually doing a call several times. It actually replaced this all with kind of a loop, right? It was smart enough to see, oh, you're doing all this recursion, and yeah, so we can do this loop here that has the same effect. And so optimizers are allowed to play really fast and loose with what goes on. That kind of means that these variables stop really having any meaning. Which thing is base now? It's kind of one of the registers, sort of. All that really happens is by the time this function is over, EAX contains the result. Or RAX contains the result, not EAX. RAX being the 64-bit version, EAX being the 32-bit version. So RAX contains the result, and that's that. That's all you really know about this function. None of these variables really strictly have any relationship to any particular register at any particular point in time. They're all, the function just looks at it, the optimizer just looked at this code and kind of just did whatever it wanted to with it as long as it got the same result out the end. Well, when you have inline assembly, right, well, if you're in the middle of a bunch of code, the inline assembly might be doing something that actually needs memory that was supposed to have been written to by some of the code. But because of the optimizer, maybe that memory isn't being written to. Because as far as the optimizer is concerned, there's nothing, like it can't see inside the inline assembly. And if your inline assembly is doing something like calling syscall, well, then the optimizer really can't see inside of what it's doing. And syscall is basically kind of a function call. And so the optimizer doesn't know what needs to be. It has no model for what needs to actually appear where in memory at the time syscall is being run. It doesn't even understand it at all. And so it just assumes that it's like any other code and that it can ignore it. It's just like an opaque block that it can ignore, and it will do the right thing, and the optimizer doesn't have to worry about it. Just call it at the appropriate time, and just make sure that those instructions appear at the appointed place in the code, and otherwise not worry about it. Now, in inline assembly, there's a bunch of different ways you can tell the optimizer, hey, actually, this inline assembly needs this memory value or this variable value to appear in this register before the code is run, or whatever. It can say a whole big bunch of different things about all of that stuff. And then the optimizer, that's basically like a formal way of communicating with the optimizer from the inline assembly. Not at runtime, at compile time. The inline assembly at compile time will tell the optimizer at compile time some various facts about itself so that the optimizer can make the right decisions about what things need to be in what registers and what things need to be in what places in memory. But the syscall instruction has a bunch of really complicated rules about that, because half the time with syscall you're passing in pointers to memory. And the optimizer has some ways of saying, oh, this thing represents a pointer to memory, but how much memory? And where is it? Do you have to make sure that everything that is supposed to appear in memory appears in memory before this is called? Well, probably not, actually. And so it would be really nice, and there are ways to do this, to tell the optimizer, hey, this memory region here needs to be have its contents be what the standard model of running the program says the contents of memory should be. So if it looks like there was a write to some kind of place in memory, that write has to actually appear. Oh, I'm getting spam. So let's check on this spam here and immediately ban this person, because that's an unforgivable offense. No, you're not allowed to spam my chat. So there. And also the whole cheat the Twitch algorithm by having fake viewers thing. I don't like that idea. That's what the spam is about. So doing this laboriously, hand rolling it for every single system call, because I'm wrapping system calls with this inline assembly. I know the system calls in detail. Like I can look up the system calls and I know which bits of memory need to be updated to reflect the program model of what should be in memory at that time before the syscall instruction is executed. And I need a nice way of transforming that and turning it into inline assembly. Unfortunately, the templatizing engines don't allow you to generate inline assembly with a template. And I doubt that the C++ standards committee is going to say anything about inline assembly with regards to the new C++ introspection capabilities. So we'll have to figure out what to do about that. One of my ideas has been to just tell an LLM, hey, I have a bunch of stuff that needs these rules applied. Please generate all of these wrapper functions for me that do the appropriate things with regards to memory marking. And just generate all of the stuff. I don't know. Maybe that's the right thing to do. Maybe it's not. I'm not sure. Because one of the other things also is you have to tell the optimizer that, after this inline assembly is executed, the contents of this memory is now going to be different. So any program code that looks like it's referencing that memory, you have to reload the contents of memory for it. You can't just say, I loaded the contents of that memory location like 500 instructions ago. I don't need to do it again. It's in register 5, right? No, it's not in register 5 anymore, because memory got changed, and so the contents of register 5 are out of date. And so, that's another set of things that you need to communicate to the optimizer. I just did this as a demonstration that the code that the optimizer generates has only a passing resemblance to the code that you wrote here. There's clearly two function calls here, right? Do you see any function calls in here? There's no function calls in here. It completely eliminated the function calls and was able to do it all with looping, which is totally reasonable. There is a completely reasonable way to write this function using looping. And the compiler saw, you're using recursion, but in fact, you can use looping, and it will be a lot cheaper. So I'm going to switch your code to using looping. And it was smart enough to know, for example, that this division by 2 here, that's a shift right? And all of that stuff. It was pretty smart about what to do here. I'm actually trying to parse out what it's doing now, although that's not that important. I think actually RAX gets updated with something. Does this IMAL instruction regardless, which is kind of amusing. It just straight up does an useless IMAL that's most of the time that's an IMAL that most of the time is useless. But of course it it doesn't matter. And sometimes it is useful. Well, not most of the time. It'll be useful sometimes and not useful other times, and it doesn't know. What it does do is it does the IMAL regardless of whether it's useful or not, and then it saves the result if it happens that it's going to be useful. I find that highly amusing that it does it that way. I mean, it's probably pretty fast to do that way. I'm guessing there might be 2 multiplier units in the CPU, and they can actually operate in parallel. And so if one is idle, it doesn't really, versus being used, what the heck? Why not just pass in new things to be multiplied to it, and then we'll figure it out later, right? So that's yeah. Anyway, let's see how well the LLM is doing. Oh. Well, let's look here. Here we go. Changes. So it has the tokens. It isn't doing it quite correctly. But it's not wrong. These do work, and this will actually test the thing that says it's testing. It's just when does it create the token list, right? And this is yeah, these changes look, as I said, they look okay. One thing I kind of don't like about them, I do like that they're doing this with the semicolon, that's kind of nifty, is that they're putting it inside here. And mine had the token list created as part of the test input data out here. I don't think it matters that much, but it's okay. It's okay this way. And it's not changing the strings, so that's good. It's not cheating, because that would be one thing the LLM could do, is it could cheat and change the input strings instead. It recognized that it need to change these. Recognize that this one it's supposed to throw an it's not the same right kind of test. Yep, change this one, change this one. Now it's going to actually try and build it. Come on, it's not that hard to do this. What the heck is going on here? What is it doing? It's actually done with the command. It's done with it. What happened here? I think I'm going to need to tell it to stop working. So I think I'm going to need to tell it to do. I don't know why it's gotten stuck. Okay. So we're going to close this, close the Junie terminal. Let's look at the diff here. Notice how none of the strings were ever changed. Yep. Let's try running the tests ourselves. They all succeed. Okay. All right. So Junie kind of did it, but sort of hitched up and didn't quite do it right, or kind of stopped in the middle. But otherwise, its work was acceptable. It wasn't exactly what I wanted. What I wanted was all of these. This part, no. This part here was supposed to be up there. So this part was supposed to be there, because this is where I'm initializing all the test input data. This is part of the test input data. But it's not that big a deal. It's not that big a deal. And it was smart enough to notice that that some of these things were supposed to fail or aren't that kind of a test, and it doesn't need to do the comparison. It did a pretty good job overall. As I said, just that one little detail that I wished it had gotten correct. And I don't know how I could have told it midway through, hey, you're not doing this quite right. I want you to correct it, please. Anyway. Well, that big refactor was mostly letting an AI agent do things while I rambled on about other stuff, showing you things with Compiler Explorer. I also outlined my plan for what I'm going to do with regards to handling static scoping and then the call stack, which I'm actually not going to have a call stack at all. The simple evaluator doesn't need a stack right now. If it ever has functions, yes, it will need a stack, but it doesn't right now, and so it doesn't need a stack. The parser needs a stack. That's what needs the stack. And I'm going to have to find a way to pass that context information along inside the parser so that the parser can do the right thing with it. The parser right now doesn't have any context information at all about what it's parsing. So that's going to be something of a change. And there I'm going to have to change the way identifiers work so that they are now referring to some kind of abstract representation or abstract identifier rather than just simply be the name, which is the name is just a pointer to something that gets resolved at runtime with the way that I currently have it. So, yeah, I had that plan in place. That plan is going to take quite some time to execute. I only really have another half hour of doing stuff before I have something else I have to do. So I think this refactor and all this explanation is going to have to be what the stream is today. Seeing Junie at work was kind of interesting. And I also got to hand wave and explain a bunch of stuff about C++ and programming languages in general. Anyway, I hope it was all interesting for all you. I wish y'all